Hello everyone. I hope you are doing fine. So I welcome you to this sixth session of the current problem solving session series. Subject controls manufacturing. A starting discussion of our last week's assignment program. And shifting to discussion of some program concepts. Week 6 content. This is Ranama. Start. First question was which of the following actually metal removal process. You know, there are two types or three types of manufacturing processes: subtraction processes, then additive processes, and then shape changing processes. Which are, there you have casting, you know, extracted extrusion, which again constant volume manufacturing process, and then you have print additive manufacturing. Boring is something in which material is boring is a material. So our next question asked in this particular relationship, had derived this relationship in the early class, can refer to the last video and tangent of shear angle phi equal to r ratio cos alpha by 1 of r sine of alpha. Alpha is the rake angle, phi is the shear angle, r is the chip thickness ratio or cutting ratio. It is also called as cutting ratio. The next question was the following is true for shaping process. So you know, shaping process is also called an intermediate process. Why? Because the cutting tool is two cycles, one cycle, and then you have a one cutting cycle in which the tool actually moves back initial position. Then again the cutting cycle starts. So it is an intermittent cutting process. So option B is correct. A says a tool is provided and reciprocating is provided. So option A and B both correct. Next question asked for rake angle alpha, shear angle phi, and friction angle beta. The equation is given as phi plus phi plus beta minus what is equal to pi by 4. Dash in case of Stabler's relationship, Schaeffer's theory, gap here simply alpha, it is related to rake angle. So shear angle and friction angle is there. So you are left with rake angle. The rake angle varies as alpha and alpha by 2 in the Stabler's relationship and Lee-Schaeffer theory, respectively. So option B is correct. So for Stabler's theory, it is alpha by 2. Schaeffer's theory. Then you have the tool wear question, a tool about upmilling and downmilling, right? So upmilling, the tool is given an opposite motion with respect to the workpiece. So tool and workpiece actually moves in opposite direction. And so what happens is once the tool starts connecting the workpiece, and there is a sudden interaction, and then the cutting force gradually increases. The cutting power also increases, and because there are staggering in cutting forces, so there is also larger in case of upmilling. Downmilling generally results in significant less tool wear compared to better chip reduced cutting force because both forces are moving in the same direction. I hope this is clear to you. Let's move to the next question. It says in an orthogonal cutting operation has a rake angle of yields a deformed of 0.6 millimeters, and the friction angle in case of stand Merchant theory is 45-degree, while it is 30-degree in case of Lee and Schaeffer theory. So there are two differences which are given. Then the chip thickness before cut has to be found. Now, the variation in the Ernst theory and the Lee Schaeffer theory. The Ernst theory, it is pi angle b alpha is equal to pi by 2, whereas in Lee Schaeffer theory, phi plus beta minus alpha is pi by 4. Now all the values are given to you. Just have to plug in the values and see the chip, uncut chip thickness. Thickness of chip before cut has to be found out, or the uncut chipness at T1. Okay, just plug in the all the angular values here, and you can it's coming as 0.11. So you can cross check both the theories, and if value is coming similar, then it's all right. Otherwise, you have to find both the theories separately. 0.31 same for, and option 1 is correct here. Question asked to find shear plane angle and the shear strain machining or operation where the chip thickness before cut is 0.3, cut and undeformed and after cut is 0.6. So the rake angle is again 20 degrees. So shear plane angle, shear strain of the machining operation. So we had derived the equations in the you have also gone through them in your regular classes. Just plug in the values in the standard formulas. Tan of tangent of the shear angle phi is equal to alpha by r minus sin alpha. So here r is the ratio, chip thickness ratio. So simply plug in the values and you can find phi as 29.53 degrees, right? And the shear strain is simply 10 of the shear angle, rake angle plus cot of the shear angle, 2.747. Hope these questions were quite easy for you to solve assignments. Let's move to the next question. Said which of the following is true while tracing a cylindrical surface? So that geometrics is for circular and straight line. And is correct here. Then if the coefficient of friction while machining is 0.5 with rake angle of 20 degree and thrust force is 500 Newton, then you have to find the cutting force Fc. Now the coefficient of friction, is given by the ratio of friction force to normal force, right? Just have to replace the forces, unknown forces, friction and normal in terms of the known forces, Ft force and that force is given here. The angle alpha is also given, and find out the Fc is equal to 4. C is correct again here. Right. Next question is again a numerical problem where you had to find the friction angle, Ernst and Merchant Schaeffer's theory. Peak angle is 20 degrees and the shear plane angle is 5 degrees. Shear plane angle is 45 degree. It is given. Theta friction angle is given as you have to find out. Angle is given as 20 degrees. Ernst and Merchant's theory. Friction angle is 20 degrees. Lee Schaeffer's theory. So option D becomes correct again here. Solved this kind of small problems in your assignment questions. Discussed much larger problems in our earlier classes. If you have any doubt, then we'll discussion of some of the questions out of your current week's content. Have any doubt, you can please ask. Okay. Right, so let's move discussing some of week six's content, some of the problems. A numerical question I am giving you in terms of plastic deformation and resulting heat generation during machining processes. Uh, so the question asks you to determine the temperature rise in the primary deformation zone, secondary deformation zone, and hence the maximum temperature generated during machining of mild steel. I hope you are already aware about the different deformation zones that are prominent during machining process. So the heat generation during machining is mainly because of the plastic deformation, right? So there are three different deformation zones depending upon the intensity, the primary, the secondary, and the tertiary, depending upon whether the interaction is with chip, uh, chip and workpiece and tool. The primary deformation zone is where there is an interaction between the tool and the chip. There is secondary deformation zone, the chip and the workpiece, and there is uh, tertiary deformation zone between the chip and the workpiece. Last deformation zone and workpiece generates the least amount of heat because the tool can be designed in such a way that the nose radius is minimum, then it is pushed up so that there is very little uh, area of interaction between the and the workpiece. Tank wear is again minimum, and hence is also. But the main significant deformation zones which leads to a significant amount of heat generation and hence temperature rise are the primary and the secondary zones, right? Primary zone is where the tool interacts with the chip, surface interacts with the chip, and secondary is where the workpiece, a shear surface of the workpiece interacts with the chip. So in this question, you have to find out the total amount of heat generation in the primary and secondary zone, and you can simply find out the temperature rise out of these heat generation equations. Once you have found out the temperature rise in the primary and the secondary zone, you can just sum up it with the ambient temperature so as to find out the total temperature rise in the I hope I have given you a rough idea about how to solve this problem, and then then some time to I solve this question. Then we'll the solution in detail. Just give it a try. We'll look into the solution to this question right away. As I discussed, the question asks you to find the temperature rise in the primary deformation zone, a secondary deformation zone, temperature generated. Find out the heat generation first in both the zones, and then temperature rise will come up, then you can just sum up all the temperatures in the primary zone, secondary zone, and the ambient temperature to finally arrive at the total temperature rise, the process, current machining process. So now, as per the given data, of the rake angle is 0 degree of the cutting zone is 1.5 millimeters. Cutting velocity is 1 meter per second. But chip thickness is 0.3 meters. Coefficient of friction density, capacity, ambient temperature, shear stress, everything is provided. So let's start finding out the shear angle first. So in this question, you have the rake angle, but shear angle, shear angle, can find that using Schaeffer's principle. So phi is pi by 4 minus of tangent of friction coefficient 0.3 friction angle, and rake angle is 0. So the total shear angle is 28.30 degrees. Now you have to find out the heat generation, plastic heat generation, that you need cutting force value primary zone, because the heat generation in the primary zone owes to the cutting force and the cutting velocity factors. Again, in the secondary zone, it is related to the chip velocity and the friction force between the chip and the surface. Okay. Now here you can find out the shear force, which will then be for in the next step, find out the cutting force value. The shear force, is given by the shear stress multiplied by the net effective shear area. So here it is width of cut W 1, and uncut chip thickness divided by sine of the shear angle gives you the net effective surface area divided by shear stress. You will get the shear force is 379.67 Newton. Now you can find out the cutting force, which there is a variable part, right? So this F is by cos phi plus lambda minus alpha. This part is nothing but resultant force. Let's replace it in terms of shear force value, the cosine of the combination of all those angles, right? Now you know all those values. Shear force we have found the last step. You have a friction angle. Angle is given in the pro, and the shear angle phi has also been found. So totally you can find out the 510 newtons. Then you can find out the chip thickness ratio R as sine phi by cos of phi minus alpha. This has been derived out of relation between the shear angle, rake angle, and the chip thickness ratio R. We had derived it in our earlier class. Chip thickness or cutting ratio R is given by sine phi by cos of phi minus alpha. You can just plug in the values of phi here. So phi has been found out in the last part as 28. Then cos of phi minus alpha, alpha is 0 degree, 0. So just plug in the values to find the ratio as a 10 phi is 0.53. So now we are at a point to find the thrust force, F tangential force Ft as Fc tan of lambda minus alpha as 150.71 newton, and then you can find out the friction force chip and the as Fc sine of, or between the chip and the work, Fc sine of alpha plus Ft cos of alpha. So all these equations and formulations has been derived out of the motion cycle diagram. Seen it in our regular classes, and have also discussed it to some extent in our problem solving classes. So I'm not going to the details right now. Simply I'm showing you the steps to solve such problems. So now you can find the friction angle. So sine of right angle is 0. So sine of 0 is 0. That means left out with the ft cos alpha, and cos of 0 is 1, so this becomes equal to ft, which is 71 newton. The angle is 0 of the friction force as a actual force, 152.71 newton. So now you can find out the heat generation in the primary and the secondary zones as del E is equal to total that is carried away with cheap fully generated is cutting force city, uh, and the negated part is the heat which has been taken away with the chip. It is the action force multiplied by chip velocity. Okay, just plug in the values again from the earlier derivations from by using sine rule. Have seen how we have in our last class we have seen how we have derived the different velocities, the chip velocity, the shear velocity in terms of the cutting velocity v. And just refer to that earlier. We see how vc becomes equal to the chip thickness ratio or cutting ratio r multiplied with the cutting velocity v. Now we can simplify this equation taking fc minus fr into bracket and plugging in the values to see that the total generated in the primary deformation zone is 429 watts. The secondary zone, it is simply the product of the chip velocity and the friction force between the chip and the generation is here simply 81 watts. Okay. Once you have found out the heat generation in both the zones, you have to find out the temperature rise, right? For that, you will need dimensionless constants. Thermal number theta, one is lambda. Right? So these kind of dimensionless constants are actually uh, uh, these are not derived, so these are actually find out how dimensional is. Perhaps you can see that the net temperature rise actually depends upon this dimensional constant lambda again depends on this thermal number theta. Okay? Parameters such as density, heat capacity, velocity, cutting velocity, T1 and chip thickness and K thermal number, then we study to find and using that thermal number dimensionless constant lambda as 0.15 natural log of 25 upon theta 10 phi. Okay, so theta you have found out to be 0.9. Plug in the value. I was steps, so let become 0.12. Once you have found theta and lambda, you can go ahead finding the temperature rise in the primary and secondary zones. And the temperature rise lambda T1 W, right? W is the width paper. Can you imagine that? Plug in the values minus point generated in this. Then plug in the C cutting velocity V, T1 and W, and see that the total is to 58.9 degrees centigrade primary zone. Similarly, temperature rise in the secondary deformation zone can this is the heat the net generated secondary deformation zone. W is the width. Rest of the parameters you know. Simply plugging in the values, you can find the generated in secondary zone at 0.97 degrees centigrade. The total temperature rises again the ambient temperature also not plus contribution from the ambient, then the temperature rise in the plastic in the primary deformation zone, and that in the secondary deformation zone is given by 522.7 degrees centigrade. That is how you solve this kind of problems. Simply and next if you have any doubt, you can ask. Just take a note of the flow, kind of. So if you're able to understand this, solve this problem, any solving type of question out of plastic deformation, heat generation, and temperature rise problems. Uh, Now we pro perhaps in one scale pro hidden concept during presentation. Then now some questions out of life questions, and finally we problem out of welding operation. Let's proceed. Let's see one question from questions. Says that you are machining steel and have one tool uh, for steel having BT6 so and point exponents, okay, Taylor to life equations, and then the tooling time is equal in both cases. It is 3 minutes. So you have to find out which tool will their production rate. There are two types of considerations. One is production rates, their production rate. One is time, it's cost. Sorry, for a high production rate, you have to find out which tool will give their candidates. Okay, so just have try to solve it out. See the solution. Alright, now if you have tried out this problem, see the solution. So the tool life equation was provided for two different kind of tools. One is tool 160, the stated power is equal to 8. You know, for higher production rate, the maximum cutting speed from production rate given by this equation. So n exponent and then k1 k2 upon n tr. Tr is nothing change in time, and n is the so the constant k1 k2 power n can be taken out as a constant c. So the net simplified equation becomes p star equal to n upon minus 1 upon n upon 1 minus n multiplied with changing time tr and n. Just put the values for both the tools. The first one n is 0.1, second one is 0.16, and c is 60, constant is 60 for the first tool, 85 for the second tool. Just putting in values, you can see that tool higher optimum speed. So higher optimum speed of this time taken and hence higher production rate will be obtained with this tool. So I hope this concept is clear. How you can play. It's clear to you. We'll move to the next question. Is again related to tool life equation. So here the well and size LW is given, cutting speed V ft by this following relationship, where LW is equal to 56.5 into 10 raised to the minus 8 and V to the power 2 to the power 0.6. Okay. So it says you can assume LW as 1.5 mm as the failure criteria, and the tool failure criteria, so it remains same across any tools. Okay. Have to obtain the tool life equation and evaluate the for a tool life of 30 minutes. Just give it a try and then discuss the solution. If you have any doubt, you can please try. Let us look at the solution. The well end size was found to depend upon the velocity and time as 2.1.6 exponents. It has been said that take 1.5 mm the well end failure criteria. Just assume that uh, is the criteria for tool failure and it remains constant across. So the tool action obtained from value and can evaluate the cutting speed 30 minutes. LW equal to star, it is 1.5 mm. We get V to the and 4 T to the power 6 is equal to 5 upon 56 5 into 10 raised to the power minus 8. This comes from this particular equation. Now from that you can simplify this out. Say VT 5 equal to 5 is the tool equation. Value of T to find out speed 30 minutes. Well, find that speed at 30 minutes is 6 meter per minute. This was the simple catch. Replace the and assume this to be the tool. So if let's proceed to our next question. The question is again about tool life patience. So here during machining of mild steel at a cutting speed of 40 meters, an HSS tool of given tool geometry where the angle is 30 at cutting edge angle, and then which was up 40 minutes with a tool life at 60 meter for an HSS tool of uh, 15 degrees at cutting edge angle. Then realize that from the tool geometry given, the tool signature given. Now the constant C for the Taylor's tool life equation is given related to the side cutting edge angle as C equal to 78 gamma plus 15 whole raised to the power 2.26. Okay, is given. You have two cases. In one of the cutting speed as well as the tool life given in terms of minutes, and in the other case the cutting speed is given. You have to find the life. Try and discuss the and then actually build this solution. Alright, so the side cutting edge angle is varying for both tool and degree for the second tool. Again, you have 4 meters per minute tool and 60 meters per tool. The time of cutting is given as 40 minutes for the first. You have to find that for the second, right? Simple, just replace values and find the constant using all the parameters for the first tool. So C, you can find out 9.86. Then just use that particular C. Uh, the second for the side cutting edge angle of 15, find out the C value to be 6. Now you can use the Taylor's to life equation as exponent n can be just as log C by V upon log of T. Just replace values case and then value to be 0.49 and just use that particular find the tool second case. It's 12.86 minutes. That is simple, just through it. Then we do some building questions. So let's see what questions now as we're moving to sessions. DC arc welding arc length characteristic was obtained via 5 L. So L is the arc length varied between 5 millimeters and 7 millimeters. Now arc voltage V is in volts and the arc current was varied from 400 amperes to 500 amperes. Now assuming linear power source characteristics, the open source circuit voltage and the short circuit current operations are to be found. So for linear power source characteristics, this relation holds where VR is the arc voltage, OC is the open circuit voltage, I is the current, and SCC is the short circuit current. Summation of all this equal to 1, so I'm not of how it is found. Must have seen that in whatever so think this relation true, you can try to find out the OCV SCC using all those relations. So this is the arc characteristics, arc length characteristics, and source characteristics. So 2 points have to be added. You can see the variation of length and the variation of current. Okay, let's try to solve this problem. We'll see the solution. Okay, let's look at the solution now. The voltage arc length characteristic was obtained as 20 plus 5L, right? So V arc is 20 plus 5L, and length has been varied from 5 mm to 7 mm. At the same time, current was varied from 400 to 500. So when L was 5 mm, the current was 5 ampere, right? Now, V arc can be equal to 20 plus 5 into L, replace L with the length 5. It becomes 45 volt, and then current was 500 amp. Same time when length was 7 mm, so the current was right to 400. So for one length you have 5 ampere, for the length 7 mm, current is 400 amp plus 5 into 7. 7 is the length, the arc length. So it is 5 volts. So you have two sets. One is for 500 ampere. You have the second set is 55 volt. Just plug in the values. You'll see two equations. You'll arrive at two equations with two variables, so CB and SCC, unknowns and two equations. So you can solve these two equations to find out CB and SCC. Just simple rearrangements. Equation 1 by 4 and 5 as OCB is 95 volt, and then short circuit current SCC is 950 amps. Okay, simple as that. Try to understand this. And this is the last question. We'll move last problem of today's session. It says MIW gas metal arc. The power source characteristics is given by Vp 6 minus I by 60, where I current. Okay. Arc characteristics is given by Va is equal to twice of length La plus 27. Now Vp and V are uh, I is the current, I is the arc length, La, sorry, arc length La meters. The change in power volt amperes of the arc have to be found out. Arc length is changed from 3 mm to 4. Try and then The solution as shown, power source characteristics has been given as Vp equal to 6 minus I by 60, right? And arc characteristics has been given in terms of arc length as twice La plus 27 equal to Va, arc voltage. So just equate these two, then you can find uh, current value I in terms of the arc length value versus characteristics, and then the arc characteristics. Just equate these two, you can find out current in terms of La. So current becomes 60 into 9 minus twice of La. Okay, so just you can multiply these two, then find out the power, and plug in the values of arc length as separately. First one is 3 mm, second one is 4 mm, to find the power in the two cases P3 and P4. You can find the difference as 3840 volt ampere. So I hope this clears all your doubts, or this helps you. This will help you solve some of the problems out of your assignments, next week assignments too. I hope the assignment questions for next week has also been discussed and clear to you. So I will stop here with this session. If you have any doubts, so sometime.